Hey there, welcome to the examples video for section 2.3. Here we're going to cover motion and velocity, motion and space. And we'll start with problem 1 here, which is essentially computing some derivatives and magnitudes. So we're given the position vector of an object in the plane. So it's a planar motion, it will just have an I and j. And it's given with a t cubed and a t squared. They ask us to find the velocity vector at time 1, the speed at time 1, and the acceleration vector at time 1. Then we have to sketch the path and everything in there. So first off, it might actually be helpful to understand later on for the sketching what kind of curve this is. So we have t cubed, t squared, and if we put in a t here, maybe we'll recognize this as the twisted cubic. So it's good to know those examples. And then if we are looking at the twisted cubic without that, then we're looking at the projection into a specific plane. And this is actually going to be the YZ plane here. So we have that if this is x and y, then y cubed is equal to x squared, right? Because you cube the t squared here and you square the t cubed, and they both end up being t to the 6th power. So that's the relationship we have between these things. And then this tells us that we have x equal to y to the 3/2 power, which looks something like this, but then we have the bottom part as well. And so this would be the y and x axes here. Okay, so that's just for us to sketch things later on, but now we have an idea of what our path is going to look like. And we can go ahead and just compute some derivatives. So given r as t cubed, t squared, we can get v, and the derivative is going to be 3t squared. Remember, we do this component-wise, comma 2t. And I know I'll need my acceleration vector. Actually, let's compute the speed first. So the speed is going to be the norm of the velocity vector, and that'll be the square root of this squared plus this squared. So 9t to the 4th power plus, use it in a little bit, plus 4t squared. All right, maybe we can simplify that just a little, factor out a t, and we get t square root of 9t squared plus 4. Okay, and actually I want absolute value of t in front because square root of x squared is absolute value of x. We need to account for both the positive and negative solutions. Okay. Now the acceleration vector is the derivative of the velocity vector. If you remember from our formulas on the previous video, we get 6t, 2, and this may look familiar from computing derivatives with the twisted cubic. Okay, so that's everything that we need, and we need to just plug in 1 for a lot of these things now. So v of 1 is 3, 2. The speed at 1 is, all right, absolute value of 1, square root of 9 plus 4, and this is just the square root of 13. And the acceleration at 1 is the vector 6, 2. Okay, so now we have to graph this. All right, so I'm going to draw our standard coordinate system with x horizontal and y vertical. And we need a relatively big one here. But because I did that work earlier, figuring out what my vectors look like, or sorry, what my curve looks like, I know in general what my curve should be drawn like. Something like this, sort of a vertical cusp right there. All right, and this is the y-axis now, and this is the x-axis. All right, so my curve is then going to be moving in the positive x direction. As t increases, so does x. All right, and let's see, maybe I need the position vector as well, because otherwise I won't be able to tell you exactly where to draw the velocity vector. So I get position 1, comma 1. Okay, and that should be somewhere around probably here. Okay, so there's our position 1, comma 1, right it over here. All right, and now I can start drawing in my vectors. So my position vector goes from the origin to that point. Okay, that's r of 1. My acceleration, or sorry, my velocity vector is 3, comma 2, and so that starts here and moves out, and it says for every 3 units in the x direction, I go up 2 units in the y direction. So something like this. It's probably not super accurate, but it's close. All right, and then last is the acceleration vector, which is pointing in this direction. That doesn't seem quite right. 6 in the x and 2 in the y. Oh, it's not, okay. So our acceleration vector is then going to be twice the length of this. So I'm actually going to start shrinking things a little here. Shrink, 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 shrink. And then place things here. Move that one as well. And then I'll put in my acceleration vector, which maybe I should make smaller. Should go something like this now. So it should be about twice as long and twice as long in the x direction, about the same height in the y direction. Okay, and so now we have our position 1, 1, our velocity v1, and our acceleration a of 1. And that's it. So we've sketched our path and all of our vectors as well. The velocity, or sorry, the speed is just the length of this vector. So that's the square root of 13. The acceleration speed doesn't have a, or the size of the acceleration doesn't have a name, but it should be, what is that, square root of 36 plus 4, square root of 40. Okay, and so that's longer. You can think of like a triangle right here. All right, moving on to problem 2. Let's see what we have. Sorry about the zooming in and everything. So next we want to find the velocity, speed, and acceleration for a particle with this motion function. Okay, again, nothing special there. We just want to compute some derivatives. We have our position function given already. Our velocity is just going to be the derivative of that. So we need 2t e to the t, and then the derivative of t e to the t is 1 plus t e to the t. Okay, our norm then is the speed, and so that'll be the square root of 4t squared plus e to the 2t plus 1 plus t squared e to the 2t. Okay, and then we can simplify this a little bit. 4t squared plus 1, 2 plus 2t plus t squared e to the 2t. I just combined these two terms right here. And there's our speed. The acceleration then, let me actually make this over here, is the derivative of the velocity. Acceleration, derivative of the velocity. And so that's going to be 2e to the t, and take the derivative of this thing again, and you should get 2 plus hold on, 2 plus t, I think. E to the t. Yes. And so there's our acceleration function, and that's it. Third, we have a particle. Its initial position is given. Its initial velocity is given. And we're given its acceleration function. So what do they want us to do? They want us to find the velocity as a function of time and the position as a function of time. Okay, so here's our acceleration function. And we know that the acceleration is the derivative of the velocity. And so the velocity should be the antiderivative of the acceleration function. And you know what, I'm going to make that smaller. So the antiderivative of the acceleration function. Except I need an extra factor because I need to anti-differentiate both sides, or integrate both sides. And so I'll get v of 0 right here. Okay. And if you don't know this already, there's a trick you can do where instead of finding an antiderivative and then solving for c, you can set your lower bound to the initial parameter and your upper bound to the variable. Change the inner variable, call it s maybe. And now when we do this integral, we get the answer right away because we're given v0. So that saves us having to find c, the constant of integration. Okay, so we have v0 right here plus the integral from 0 to t of our acceleration function, 4t, 6t, 1. Oop, that should be an s. 4s, 6s, 1 ds. And now, if I integrate that, I get, let's see, 2s squared, 3s squared, s, and I'm going to plug in s from 0 to t. All right, now I know plugging in 0 is going to give me nothing. It'll just give me the 0 vector. So I only need to replace s with t and then add it to v0, and I'll have my velocity vector. So here I have 1 minus 1, 1, plus 2t squared, 3t squared, t. All right. And if you want to write that as a single vector, that's fine. I'm okay with the way it's written already. We can do this. So minus 1 plus 3t squared, and then 1 plus t. All right, so there's our velocity vector. Next, we need our position vector. And yet again, we know that the velocity is the derivative of the position. And so we, to find the position as a function of time, we do the same trick. We integrate from 0 to t. And what are we integrating? The velocity function with a different variable in here as a dummy variable, so that we don't get confused between this variable and the actual variable of integration, or sorry, the actual variable of the function. So here we've got, what's R0? I think it's 1, 0, 0. Yep, so we're given our initial position here, plus integral 0 to t of the whole thing that we just found. 1 minus 1, 1, plus 2s squared, 3s squared, s, and then ds. All right, and we can do this integral. None of the integrals in this section should be particularly hard. They're just there to show you how to actually do the calculus, or how to set the problems up. All right, so again, if I integrate this, I'm going to get polynomial here, polynomials there, and I plug 0 into those. They have no constant terms, and I will just get 0 out. So all I need to do is integrate these by finding the antiderivatives, and then plug in t for s. So let's see, we get s minus s, s, plus, what is this, 2/3 s cubed, and 1/2 s squared. And then just plug in t. All right, so we're almost there. 1, 0, 0, plus t minus t, t, plus 2/3 s, or t cubed, 1/2 t squared, and that's it. We can also write this as a polynomial now, so this might be kind of interesting. If we were to separate out all of the vectors with different powers of t, we would have 1, 0, 0, plus 1 minus 1, 1, t, plus, all right, now I need to split this vector into two pieces because it contains parts that have t cubed and parts that have t squared. So I'll write 0, 0, 1/2 t squared plus 2/3 1, 0 t cubed. And so now this is a polynomial with vector coefficients, which you can think of as a system of 3 polynomials if you want. But that's it. So we have found our velocity and position as functions of time. And we did it just by integrating from 0 to t on both sides of the defining equations for acceleration and velocity. All right. This will be the last example for this video, and then we'll make a second one. So we have an object of mass m is moving in a circular path with a constant angular speed of omega. Okay, so the angular speed is related to the actual speed, but they're not the same. And what do they want? Well, they've also given us this position function. Notice that it is in the plane. It's a circular path. It has to have no torsion. And they say, find the force acting on the object and show that it is always pointing towards the center of the circle. Okay, well, let's see. The force, by Newton's second law, okay, I can make this bigger. is given by the mass times the acceleration vector. Okay, but the acceleration vector is the second derivative of the position. And the mass is constant, so I can drop this dependency. So I just get to write m r double prime of t. Okay, and now I have things that I can compute. So m, and then the second derivative of a cosine omega t, a sine of omega t. And this is just our standard parameterization for a circle with a frequency of omega. So this tells us how quickly the circle is swept out. And I want the second derivative of that. Okay, well, I take two derivatives of cosine and I get minus cosine, and two factors of whatever's on the inside. So I have m times minus a omega squared cosine omega t, and then minus sine, minus a omega squared sine omega t. All right, so there's my second derivative. I notice I can maybe factor some stuff out here. All right, m, let's see, minus m, minus m a omega squared, and then minus, actually, let's put the a on the inside. So minus m omega squared times a cosine of omega t, comma, a sine of omega t. All right. And then what's special about this? Well, this was the thing that we just took two derivatives of. So we actually have that f as a function of t is equal to minus m omega squared r of t. And if we ignore the m omega squared for a second, note that there's a minus in front of this. So we have that f is in the opposite direction to the vector r. Well, my vector r is always pointing out from the origin. So I draw a coordinate system here, and then I draw a vector in. Here's r. Vector r of t. And then my vector f is going to act in the opposite direction. And it might act with a different length. So the vector here is going to be either shorter or longer. But it is acting in the opposite direction, and that is for every value of t here. So the force is always acting towards the center of the the center of space, because that's the center of our path. So we choose our path to be at the center, or to be around the center, and our force acts opposite to that. Okay, so hopefully that's relatively straightforward, and we'll cover some more examples in the next video.